Hello, everybody. We are going to be doing another screencast lecture. The topic is phase changes, and in particular, we will be discussing freezing. A quick review, a topic we make sure we have to know is that we remember that phase changes is all about changes in thermal energy. So energy needs to be absorbed or released for matter to change from one state to another. Like, for example, before we talked about melting, you need to add thermal energy to ice cream to get it to go from a solid to a liquid. The different phase changes that we're going to be studying in this unit are shown here on the screen. And of course, like I just said, today's topic is freezing. Now let's talk about freezing. Freezing is defined as the change from a liquid to a solid. When we think about freezing, we typically think of things like ice and snow and all kinds of very cold days and winter. So is something that is frozen always cold? Well, if you think about the definition, it's a change from a liquid to a solid. Well, if we have liquid molten iron, that will change to a solid at about 2,800 degrees Fahrenheit. Most people would not consider that be very cold. But again, when we're talking about temperatures, things are relative. Object is frozen at 2,800 degrees Fahrenheit. So the freezing point is defined as the temperature at which a substance changes from a liquid to a solid. So here's molten iron, pouring it into a mold, and as soon as it starts dropping below 2,800 degrees Fahrenheit, it's going to start solidifying and forming solid iron. Here's a video clip showing how to cast a small iron cooking pot. I think it's very interesting.
Closer to producing liquid metal. But for that liquid metal to be turned into a cooking pot, there's one last process they need to master with the help of self-taught expert Colin Peck.
Hello, Jerry. Nice to see you, mate.
Green sand casting. Green sand means damp sand. When you compact it, you can form it into any shape you want. The inside of Guy and Maeve's boiling pot, for example.
What do we got? A little bit firmer than that. Work your ways into your corners.
Green sand casting was another British invention, patented by that man Abraham Darby at the start of the 1700s. Green sand was cheap and you could use it over and over again. And with it, large-scale production of cast-iron objects like bridges, steam engines, and even girders to build factories and aqueducts began.
Give a little more effort than that.
The boys make the green sand mould for their pot in 4 separate sections.
Okay, that'll do us nicely. Where to now?
But one slip as they put the sections together and the mould will be wrecked.
Oh, massive.
Once the parts are all joined, they leave a pot-shaped gap between them, into which the boys will hopefully pour their molten iron.
Well done you.
Well done you.
But it won't be until they break the mould apart at the end that they'll discover if what they've made is good enough. After days of work, it's time to break open the clay seal at the base of the furnace. As Guy stands ready to release the liquid iron, Colin moves into place with a red-hot crucible heated in his own mobile furnace, ready to catch the boys' precious metal.
She's put it up a fire driver.
She's coming! She's coming!
Success! They've made molten iron. Or have they?
Scoop it in.
It quickly becomes clear that there's a problem. The metal isn't liquid enough to flow properly.
Not hot enough.
And there's a doubt about how much is actually metal and how much is just the molten impurities called slag. It's time to act fast. Colin reheats the mix in his portable furnace and adds a healthy dose of scrap metal to make absolutely sure there's enough molten iron produced to fill the mould.
Getting close to temperature here now, so I'm going to need the mould down there.
Finally, Colin lifts the iron from his furnace and having scooped off the slag that's risen to the surface, it's over to Guy.
Right, pour away. Get in that hole. Oh, well, yeah,
Right, you got to go out the spout, guy.
This time the molten iron looks perfect, but there's still a chance it could all go wrong.
That will cool over the next 12. No, it's still molten in there. You could have just let it come out the sides.
All they can do is wait for the metal to cool, to see if disturbing the securing weights has ruined the mould, and whether Jerry's iron has done the job. If it hasn't, 2 days' graft will have been wasted.
Dump sand out of it.
The sand is removed, and success.
Want to see your pot, guys?
All right.
There you go, look, a complete pot. It's all there.
That's quite splendid, don't you reckon?
Well done, Bob. Hey?
Can't,
So very much.
can't do it without them chaps.
Right, we've earned ourselves a brew, I reckon.
Gasping.
When we're talking about melting points and freezing points and phase changes, we often will be thinking about water. So what is the freezing point of water? And you got to remember, what freezing point is a temperature. The freezing point of water is 0 degrees Celsius or 32 degrees Fahrenheit. They are both the same. Just like if you have 1 inch or 2.54 centimeters, they're the same length. If you have 2.2046 pounds, that's the same as 1 kilogram. Even though the numbers are different, it's the same measurement. Here's a thermometer stuck in a ice water bath. The thermometer reads 0 degrees Celsius, but please note that there is liquid water and ice, solid water, in the container, even though they are both at 0 degrees Celsius. Let's compare the amount of energy of solid water at 0 degrees Celsius and liquid water at 0 degrees Celsius. Which one of these choices is most correct? Is solid water has more energy than liquid water at 0 degrees Celsius? Liquid water has more energy than solid water at 0 degrees Celsius? Or is it solid water and liquid water have the same amount of energy at 0 degrees Celsius? What do you think? Well, hopefully you chose the middle one. Liquid water has more energy than solid water at 0 degrees Celsius. If you recall, we've talked about energy level. The energy level of a solid substance like water, so that would be ice, is at a lower energy level than the liquid of that same substance like liquid water. So even though they're at the same temperature, liquid water at 0 degrees Celsius is at a higher energy level than the solid at 0 degrees Celsius. Here's another video clip. Water freezing time lapse. So as we see here, here's liquid water, here's solid water. Both of them are at 0 degrees Celsius. Solid is at a lower energy level than a liquid. You must blank energy from a liquid to freeze it to a solid. So what's we do with energy? And remember, there's 3 choices that we can have. Energy can increase, energy can decrease, or energy can remain the same. So you must do what to the liquid to get it to become a frozen solid? We must remove energy from the liquid to freeze it to become a solid. There's less energy here, so we need to have this higher energy level. We need to take away some energy to get it to become a solid, to get the particles to come closer together and form that crystalline solid. Even though that there is no temperature change, it still requires a change in energy to change the state of the substance. This is 0 degrees Celsius, this is 0 degrees Celsius, but you still have to remove energy. That energy is used to either change phase from a liquid to the solid, or we could add energy to go from the solid to a liquid. Wow, I guess that's it. So that was pretty quick, and we will talk to you next time. See ya.